right-hand segment that in this manner no longer work. No longer work. Okay? So having that right endpoint of a segment is to the right of the Q doesn't help us that much. Okay? In other words, like we only know this endpoint on the right-hand side, but on the left-hand side we cannot use them. You use this fact to sort of like restrict our search. So what do we do? Okay. It turns out that, okay, there's an approach called Locus Approach. Okay, this approach actually do not just apply in this case. Okay, it can be applied in many situations. Okay, it's a more general approach. Okay, so I will describe it like you know, hopefully you can understand. So a query is described by a number of parameters. Okay, so we know like for the windowing problem, there are 4 parameters. Okay, qx prime, qy prime, right? So we have these 4 parameters. I mean, of course, these 4 parameters, you know, control where where the query window is, right? Okay, so for each choice of parameters, we get a certain answer, right? Okay, this is obvious, right? When you have when you fix these parameters, you get an answer. Okay. Assuming all those segments are fixed. All those segments are fixed. Then, if you are given a particular window, of course you get certain answer, right? That one is obvious. So often, so this is important. Okay, for locus approach to work, this fact has to be there. Okay, all the nearby choices give the same answer. In other words, okay, if a question, okay, if your problem, okay, has certain parameter, if those parameters, if a little bit change of the parameter will give you the similar answer, okay, then the idea of locus approach can be used. Okay, so if we move the window slightly, just a little bit, okay, it will often still intersect the same collection of segments, right? So this fact tells us nearby choices give the same answer, right? Okay, in a lot of computational geometry, okay, or like in a lot of questions in the real life, okay, you have such a property. Okay, it's not necessary that the question involve geometry, but of course in computational geometry, this fact happen very often. Okay, so how do we take advantage of that? Okay, let the parameter space be the space of all possible choices for the parameters. For the windowing problem, this space is 4-dimensional, okay, because we have 4 parameters, right? Okay, so because we have 4 parameters. When the problem is, you know, higher dimensional, then, you know, the locus approach is difficult to deal with. It's more difficult to deal with. Okay, so locus approach suggests partitioning the parameter space into regions such that queries in the same region have the same answer. Okay, if we locate the region that contains the query, then we know the answer to it. So it's something like, okay, say in this range, the answer is the same. So recall this for this region. When you up to a certain point, okay, we have the answer is changed to another one. So you know you have So sort of you partition your query into different regions. I mean, for each region, you may have a different answer. Okay. So such approach only works well when the number of regions is small. If you have a lot of regions, then the locus approach is difficult. Okay. For the windowing problem, this is not true because we have 4 parameters. I mean, which turns out to be 4-dimensional. So if you try to partition your space into all possible regions, there can be n to the power of 4 different regions. So which is like a lot of choices, right? So it's difficult to use a data structure to efficiently deal with that. Okay. So instead, we can use the locus approach to create alternative for the interval tree. Okay. So see, we have a new thing called interval tree. Okay. So now, okay, before we consider the original problem, let's again try to simplify our discussion. Okay? The reason we simplify our discussion is so that we can understand this locus approach, is to better understand this interval tree. Okay? So let's now only consider one dimension, just x coordinate. Okay? So that I stand for the interval. Okay? Interval be x1, x1 prime, x2, x2 prime, and so on to xn, xn prime. Okay? Be a set of n intervals on a real line. Okay? The data structure that we are looking for should be able to report the intervals containing a query point qx. So we want to report the interval that contain a given query point qx. Okay, so this is similar to, remember, I mean, in a previous discussion, we also talked about something like this, right? Right? I mean, I hope we reduced our discussion into one-dimensional. I mean, to talk about this, we reduce our problem into one-dimensional, right? Right? I mean, at the beginning of this chapter. So we are now roughly in the same shoes, okay? We are roughly in the same shoes at this point, okay? Where is it? Here, okay. So our query has only one parameter, okay, because we consider only one dimension, okay? So our query has only qx, this parameter. So the parameter space is the real line, okay? Even though the parameter space is real line, as I said, we can partition this parameter space into a number of regions. How do we do that? Okay? That P1, P2, up to Pn be a list of distinct interval n points. So let's say if we have n points, n intervals, we will have 2 n points, right? Okay, so let's put together all those n points together. Okay, sorted from left to right. Okay, the partitioning of the parameter space is simply the partitioning of the real line induced by the points pi. Okay, so it's going to be something like this. Okay, we call the regions, okay, in this partition elementary intervals. Elementary interval. So it's going to be, it's a little bit special, okay? You know, negative infinite to P1, where P1 is the leftmost endpoint, okay? So from this point to the left, to infinite left, okay? So this is one region, but be very careful. This is open, it's open end, right? The P1 is not included in this region. And then P1 by itself, this point is one region. And then from P1 to P2, without including the endpoint of P1 or endpoint of P2, is another region. And then P2 by itself is a region, and so on. So if you have n endpoints, how many regions are you going to end up with? You will have n single point regions, right? And also n plus 1, like regions in between, right? 直数问题嘛。So n plus 1 plus n. Why do we have that plus n? Because each point, each endpoint is a region. Okay? So the total would still be, you know, linear to n, right? Okay? So why do we partition the space like that? Think about this. Okay? If Qx is in here, what is your answer? Think about this. Nothing. Great. Why? Because P1 represents the rightmost endpoint, right? So that's why, okay, when Qx is here, it doesn't matter. It doesn't matter where the Qx is located. You get nothing, right? Qx is going to, you know, the interval that includes Qx is going to be empty set, right? Okay? And when Qx appear to be at exactly P1, then your answer suddenly changed to, well, it's going to be the interval that contribute this endpoint, right? Okay? And then when you enter here, well, actually, I mean, the answer here will be the same. And when you reach P2, it's the time your answer, it's the time when your answer will change, right? You can see your answer, you know, when you slide your Qx, when you slide your Qx from the leftmost, okay, to different regions, you will see that when you enter another region, it is the occasion that your answer might change, right? And only when you go to the other region, your answer will change. Otherwise, your answer should stay the same as long as your query point stay in the same region. Okay? So this concept is called, you know, the concept of partitioning the infinite space. I mean, the real line obviously has infinite choices, right? But now you partition them into a finite number of regions. And each region, you are going to get the same answer. This concept is called the Locus Approach. Okay? So with that in mind, okay, now we are in the position to talk about the interval tree. Okay. So basically, for each interval, we need to, we will associate, because remember, we want to answer query efficiently, right? So a lot of things, if we can pre-compute it, then we just do the pre-computation. But of course, we also want to make sure the computation, the pre-computation, is not too costly, right? Okay. So for example, we could get an answer for this one first, get an answer for this one first, get an answer for this one, and so on. We get an answer for each region, and then store these answers. So whenever your query point, we find out the query point is at a certain region, we just retrieve the answer of that region. Wouldn't that be very efficient? Right? Okay. But that is without the consideration of the cost. Okay, that the storage cost and the pre-computation cost. Okay. But in reality, it's especially the storage cost. Okay. See, to find the interval that contains a query point QX, we must determine the elementary interval that contains QX. So these are the elementary intervals, right? So we need to find the elementary interval that contains QX. So we build a binary search tree T whose leaves corresponds to the elementary intervals. So basically, we will have a binary search tree whose leaf nodes, okay, each of the leaf nodes corresponds to each elementary interval from left to right. Okay, so we denote this elementary interval corresponding to a leaf mu by int mu. Okay, so so this is notation. Okay, so this leaf node for leaf node, its corresponding elementary interval is called int mu. Okay, so if all intervals in I containing int mu, okay, are stored at the leaf mu, okay, then we can report k intervals containing qx in log n plus k. Okay, as I said, this is exactly what I just told you. Okay, we just do the pre-computation, and for each elementary interval, okay, we store what segments, okay, contain that elementary interval. Then pretty much when a query point falls into that elementary interval, okay, that query point must fall into the segments that contain those elementary interval, right? So we just report those segments. That's it. So it's great, right? So the query time is wonderful. It's log n plus k. Okay, but okay, so far so good. But there's an issue. Okay, the amount of storage can be as bad as quadratic. For example, let's consider this particular example. Here, okay, you can see that, okay, you have n, let's say we have n segments. Well, sorry, we use interval here. Let's say we have n intervals. And those intervals happen to be arranged like, they doesn't have to be like in the, arranged in the same space. But assume they are arranged like, from the left to the right, something like this. And if you consider, remember we use the endpoint to consider the elementary interval, right? So you see we will partition the real line into this many elementary intervals. And then think about this. Okay, you have like maybe one elementary interval that contains no segment. You have one segment that contains one interval. You have one one interval that contains like one elementary interval that contains two intervals. you have one elementary interval that contains 3 intervals, and so on. So it's going to be like a 1 plus 2 plus 3 plus blah, 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 plus n. Okay, so the complexity of this storage space is going to be quadratic, right? Okay, so this is, well, not that great. Okay, we don't consider this solution this good. Okay, I mean, we are able to answer the query efficiently, and we are able to, later on I'm going to show you how we can use this locus approach to answer like a segment with like arbitrary orientation. Okay, but at this moment you probably don't feel like, well, how can I use this to answer like segments with arbitrary orientation? But anyway, okay, that's, I mean, we'll first try to optimize this storage overhead first. Okay, so how do we reduce the overhead? Let me show you this. The solution is to store the interval at node V, okay, instead of at the leaf nodes. If that that segment go across the elementary intervals of that node's subtree, then we store. So let me show you this. Okay, so this is in this example we have 5 intervals, right? S1, S2, S3, S4, and S5, right? And we have the endpoints. Okay, these 2 endpoints are the same. These 2 endpoints happen to be the same. Okay, so these 2 endpoints happen to be the same. Okay, so we have this many endpoints, and obviously because we have this many endpoints, they partition the real line into 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 elementary interval, right? So far so good, right? Right? Okay, so you can see that, okay, we will have 15, exactly 15 leaf nodes, okay? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, there's one more here. Okay, 15. Yeah. Sorry. Okay, so we have 15 leaf nodes. Okay, but we know like each of them corresponds to one elementary interval. But okay, if we use our naive approach, if we use our naive approach, you will see that S1 will be stored here. It will be stored here. It will be stored here, here, and here, right? S1 will be stored as many leaf nodes, right? Right? Because, well, for this node, its corresponding elementary interval is here, right? It's part of S1, right? Right? And for this for this leaf node, its elementary interval is from here to here, right? So S1 includes this elementary interval, right? So if we use our naive approach, then this node has to store S1 too, right? Similarly, S1 should be stored here, here, and here, right? But, okay, think about this. Because S1, if these 2 nodes will store S1, how about we just store S1 one time here? to save the copy of S1, okay, we try to, because, well, storing S1 at every leaf node, here is not that efficient, right? We can push the storage of S1 at the parent, right? You can imagine, okay, the parent node, the intermediate node also has an associated interval, but that is not the intermediate node. For example, like this one, its associated interval is the union of elementary interval of all its children. Okay? For example, this one is represent this interval, right? This one represents this point, right? The collection of these two elementary intervals will be the interval represented by this intermediate node. And because this intermediate node, okay, the interval represented by this intermediate node is included in S1, right? So we store S1 here. Okay. For the same reason, okay, you can see this region and this region. Okay, this region is a elementary interval for this leaf node. This point region is the elementary interval of this node, right? This leaf node. So the collected interval, okay, will be the corresponding interval for this intermediate node, right? Internal node. And this region from here to this endpoint is also part of S1, right? So instead of storing S1 here and here, we store S1 here. By pushing the storage of S1 to the upper level, okay, we sort of reduce the number of copies required to store one segment. Right? But you can see that we store S1 here. We shouldn't store S1 here. You say, oh, wouldn't it be more efficient? Here, there's S1 here, right? You say, oh, we have S1 here, we have S1 here, we have S1 here. Why don't we just put S1 here instead of putting 3 nodes? Because for this node, the S1 is not included. It's elementary interval, right? So we shouldn't include S1 in here. Otherwise, it will be a false claim because S1 doesn't include this interval. Okay? So same thing can be said, okay, for S2. Okay, S2 is here, right? So you can see that, well, this endpoint, okay, has S2. And then this one, and this one have all these 4 leaf nodes, are associated with part of S2. So you can see S2 is stored here. Okay, for S3, well, from here to S3 is here, from here to here. So S3, okay, we store it here. Okay, which, well, unfortunately we cannot push further because this node doesn't. The interval represented by this leaf node is not part of S3. So we have this node to be S3, to store S3. And this one, and this one. Okay, so all these 4 nodes, okay, unfortunately, well, these 2 nodes we push up one level to store S3. This one push up one level up to store S3. But well, these 2 nodes do not have common common ancestors, so we cannot push further. So we store S3 here, S3 here. For S4, okay, S4, where is S4? S4 here. So we store S4 here. This S4, this S4. So S4 is stored here too. And then for S5, start from here to here. So we do the same for S5. So S5 is stored here, here, and here. Okay? So this is a more efficient storage manner, okay, for our interval. Okay, for our interval. Okay? So first, let's define this segment tree. Okay, the skeleton of a segment tree is a balanced binary tree. T. Okay, the leaves of T correspond to the elementary intervals induced by the endpoints of the intervals in the set I. Okay, which is a collection of intervals. Okay, in an ordered way. Okay, from left to right. So leftmost leaf corresponds to the leftmost elementary interval, and so on. Okay, so an elementary interval corresponding to leaf mu is denoted as int mu. I already previously talked about that. Okay, so intermediate node of T correspond to the intervals that are the union of elementary intervals. Okay, so basically like if this is an intermediate node, okay, I mean it's a offspring. The union of the intervals from its offspring will be the interval for this intermediate node. Okay, so the interval INTV corresponds to node V is the union of the elementary intervals INT mu of the leaves in the subtree rooted at V. Okay, so obviously the INTV is the union of intervals of its two children. Okay, this is obviously true because we are talking about binary tree anyway, right? So each node or leaf V in T store the interval INTV and the set IV. Okay, this is corresponds to like the intervals. Okay, I mean no I of intervals. Okay, so it's going to be a store maybe a linked list. Okay, and this canonical subset of node V contains the interval. Okay, x prime. Okay, such that the interval of V is a part of this interval. Then we store this interval in this linked list. Okay, and the parent V. Okay, be very careful. Okay, we store at this V, but not in the case if the parent of V, its interval is not part of this segment. So it's not part of this interval. Okay, we try to push it to the upmost, upmost level to store that interval. Okay. So, having introducing the it's a segment tree. Okay, I think it should be the name should be segment tree. Okay, a segment tree. Okay, it's a segment tree. It's not interval tree. Interval tree is the one that we talked about. Yeah. So anyway, here a segment tree on a set of n intervals uses n log n storage. Okay, so if you are able to push the storage of the interval, okay, to the higher level, okay, like what we did, okay, then the storage cost is going to be n log n. Okay, it's not going to be quadratic anymore. Okay, why? Okay, first we know that the height of a segment tree is log n, right? Because remember, okay, if you have n intervals, okay, then how many endpoints are you going to have? at most 2n, right? If you do not consider some endpoints may be shared, okay, then in the worst case, you are going to end up having 2n endpoints, 2n different endpoints, right? And for the 2n endpoints, okay, the induced elementary interval will be 2n plus 2n plus 1, right? Like I previously discussed. It's going to be 4n plus 1, right? Right? So, I mean, this is the upper bound because some endpoint may be shared, right? Okay, so at most you have 4n plus 1. For n intervals, you have at most 4n plus 1 elementary interval. Okay, and this 4n plus 1 will be the maximum number of leaf nodes you could possibly have in this segment tree, right? Because in the segment tree, each node will be be associated with the elementary interval, right? So the leaf node, the number of leaf nodes at most is 4n plus 1, right? Okay, and so the total nodes, okay, if you have 4n plus 1 nodes at the leaf node, the height will be, well, log n, right? I mean, in terms of order, okay, of course, like maybe with so it's log parentheses 4n plus 1. It's going to still be log n, okay? So the height will be log n, okay? So this is x prime, somehow like, okay. So the height of the segment is log n. So any interval, okay, and we also know any interval x prime, okay, is stored in the set IV for at the most 2 nodes at the same depth of the tree. Why do I say that? Okay, because think about this. If you have 3 nodes at the same level that will store the same interval, okay, then let's call that interval I as just call that interval I, okay? So if the interval I is stored at the V1, V2, and the V3, okay, because this interval is continuous, right? It's continuous. So these 3 nodes, they must be, what should I say, like next to each other on the same at the same level, right? Right? Okay, but which means that okay, because we are talking about binary tree, right? Binary tree. So either V1, V2 will share the same parent, or V2, V3 will share the same parent, right? So if V1, V2 share the same parent, the fact that V1 and V2 both store this I, it means that we shouldn't store I at this level. We should store I at its parent, right? So we should get rid of I from V1, V2 and store I at the parent. If V2, V3 share the same parent, then again, for the similar argument, we should get rid of the I from V2 and V3 and store I at the parent, right? So, having said that, pretty much, okay, I mean, if we create a segment tree, okay, then any interval, okay, is stored at the same level by at most 2 nodes. Okay, so think about this. We have log n level, right? So at the most, a node will be stored 2 times log n this many times, right? And we have n segments, n intervals, right? So the total storage will be n log n. Okay? Yeah. So after we finish this group, let's take 10 minutes break. We'll come back. We'll continue our discussion. Okay.